In our recent videos, we've been discussing the concept of momentum and conservation of momentum. So we've defined momentum as a vector that is equal to the mass of the object times the velocity of that object. And we looked at an external force acting on that object. If we were to integrate that with respect to time over however long that force is applied to that, we would get the change in momentum of that object. And we've defined this integral sort of as the impulse on that object. This all came from the fact that we can write Newton's second law, mass times acceleration, which was mass times the derivative of velocity with respect to time. Well, since mass, we're going to assume here is constant, that object's not breaking apart or changing its mass, we can bring that mass inside the derivative, and Newton's second law can then be written as F net is equal to the change in momentum with respect to time. And then if we integrate this side, we get the impulse. If we integrate this side with respect to momentum, we get the change in momentum. Using this and Newton's third law, we were able to define sort of a system of objects, say three objects that all interact with each other and have forces and action-reaction pairs on them. And Newton's third law, sort of what it came about is, the force on one, exerted on one by three, and the force on three exerted by one. All these forces are action-reaction pairs, which means they're equal and opposite in magnitude. If we look at the impulse from them, we see that what we showed was that essentially the change in momentum of all of those objects in our system, if we define our system in such a way that there are only internal forces, the change in total momentum of that system has to be zero. And we derived this conservation of momentum. And in the last video, what we looked at is we started to discuss collisions and how we essentially can, using this, look at our initial momentum of our system and set it equal to the final momentum of our system, and use that in a very nice way to sort of deal with collisions that are kind of too complicated to handle using the rest of the tools in our toolkit, right? If we have two balls, say, that come in and collide with each other, that force is not going to be constant. It's going to be changing with time, and we're not going to know the details of how. So using kinematics and dynamics is going to be really hard. We don't know how the energy transfer process works. Is energy conserved, or is there some generation of thermal energy, or how does that all the details of that aren't necessarily known to us. So energy becomes hard to and use to analyze these things. But for collisions and things like that, we generally know that momentum is going to be conserved in those systems. So we can just apply that conservation of momentum to figure out what we need to know. Now, there are certain types of collisions that we will know how to deal with, and we'll need more information than just this conservation of momentum. And that's what we're going to look at today, the different types of collisions. One that we've looked at already we've called inelastic collisions. These, perfectly inelastic collisions we defined as collisions where the objects stick together afterwards. So you can think of like a clay ball striking another clay ball and they stick together. Car crashes, a car T-bones another car and they stick together. That's an inelastic collision. They stuck together. A bullet being shot into a wooden block when it sticks inside. That's inelastic. What this name comes from actually is the energy involved in that system, right? So let's think about collisions. And if we look at a collision, we have some object that, moves and strikes another object. And if we zoom in and we were to sort of model this, we have all the atoms bonded together, and we can model those atoms and the bonds as springs. And when they hit, they're going to sort of bend and compress. All those springs are going to move, and they're going to bounce together like this. And there's sort of two things that can happen. In an inelastic collision, these springs and this whole, transfer of energy from, say, this kinetic energy because the objects are moving into this sort of compression and stretching and compressing of all of these springs. In an inelastic collision, that's not perfect, right? We don't have this kinetic energy goes entirely into potential energy of those springs, goes back into kinetic energy. That doesn't happen. They are not behaving like perfect springs in an inelastic collision. They stick together. We have this sort of kinetic energy converts to potential energy, but then the objects become deformed. They don't spring back, and we have a lot of that energy just goes into sort of thermal energy of the objects. They heat up. So inelastic refers to the energy processes. The objects are not behaving like perfect elastics, where we have this transfer of energy from kinetic to elastic back to kinetic energy. We can think of other types of collisions, and you may have seen this coming. There are things called elastic collisions, where we do have that transfer of energy, right? If we refer to something as a perfectly elastic collision, we end up with this kinetic energy gets transferred into elastic potential energy, or potential energy of all these sort of springs in the object. And if it's perfectly elastic, it comes back and the objects bounce apart, and the kinetic energy that we had at the start before the collision is the same as the kinetic energy after that collision, right? So these are essentially the two types of collisions we have that we're going to deal with anyway. And the nomenclature, the way we name them, refers to the energy processes in them. If they are inelastic collisions, there is a significant amount of that initial kinetic energy is dissipated and turns into thermal energy in the solids. If they are elastic, those objects end up behaving like perfect springs, essentially. And we have this very quick transfer from kinetic to elastic potential back to kinetic. And the initial kinetic before the collision of our system is going to be equal to the final kinetic energy after our system for elastic collisions. And this is a very, sort of important thing to know if we can know it, right? So if I describe a type of collision and I say this is a perfectly elastic collision, or we know it's elastic, this gives us another equation we can use, or another model sort of we can use to help figure out things we don't know, right? If you think of the inelastic collisions we've had where the objects stick together, we have two objects. Say I tell you how these objects are moving beforehand, V1 and V2. Afterwards, they stick together, as to some object and have some V final. Conservation of momentum tells us M1 V1 plus M2 V2 is equal to M1 plus M2 V final. The fact that after the collision, there's only one velocity we have to worry about because they're stuck together means there's one less sort of unknown we have to solve for, and conservation of momentum is enough to get that. In perfectly elastic collisions, they don't stick together. They bounce apart. So we would have to solve for a final velocity for both objects. Momentum isn't going to be enough to do that. So how can we do it? Well, let's imagine a perfectly elastic collision, right? Before the collision, let's just set up this situation. Before the collision, we have object one moving with some initial velocity in the x direction towards a stationary object two. Object two is not moving, right? During the collision, this is a perfectly elastic collision, so we have all this kinetic energy at the start is kind of converted into some potential energy. Then afterwards, the kinetic and energy is back. All that kinetic energy is transferred back into kinetic energy. And now we have object one moving with some final velocity in the x direction, and object two moving with some final velocity. Now, so far what we've discussed is we know this is a collision, so we know we have conservation of momentum. We know the total initial momentum, which is m1 v initial x1 plus m2 v initial x2 is equal to m1 v final x1 plus m2 v final x for object 2, right? This is the total momentum of our system initially is equal to the total momentum finally. Object 2 is stationary at the start, so this is 0. So we end up with this equation, m1 v initial x1 is equal to m1 v final x1 plus m2 v final x2, right? And that's the equation that conservation of momentum gives us. We don't know the two final velocities, though. So we have one equation and two unknowns. We can't solve this. Thankfully, though, we also know, because we've been told it's a perfectly elastic collision, that the kinetic energy at this before the collision is equal to the kinetic energy after the collision. So we have another equation, which is 1/2 m1 v initial x1 squared, 1. V2, again, the velocity was 0, so there's no kinetic energy in that, is equal to the final kinetic energy, m1 v final x1 squared plus 1/2 m2 v final x for object 2 squared, right? And this gives us our second equation that with the same unknowns. And now we have two equations, two unknowns. We're able to solve for that. Now, rather than go through all this algebra, I'll just do the first sort of step here, right? You can essentially isolate, solve for one of these unknowns here. If I were to solve for v final x for object 1, this is going to be equal to m1 v initial x for object 1 minus m2 v final x2, all divided by m1. This was just rearranging this first equation up here. If I substitute this into there, perform the square, expand it all out, and solve for it, I can actually solve for v final and v initial in this case. And what we end up with is that, right? The final velocity of object 1 is given by this, mass 1 minus mass 2 divided by the total mass times that initial velocity of mass 1. And the final velocity of mass 2 is 2 times m1 over m1 plus m2. So these equations apply for any time we have a perfectly elastic collision where ball 2, or the second object in that collision, is at rest prior to the collision. So we can immediately, and what it comes from is conservation of momentum and conservation of energy. You know, momentum is always going to be conserved in collisions, and if we know it's perfectly elastic, the kinetic energy is also conserved. Right. Now, okay, great. What do these actually mean? How do we know they're right? Obviously, you know, we wouldn't have put them in the textbook or be explaining them now if they weren't right. But one of the skills I want to highlight here of things we can do after we've just done a lot of thinking and used some principles to sort of try and derive equations that describe a situation. We want to start, you know, to think, is this right or not? And how can we do that? And some of the ways, one of the things that I think is very useful as a scientist and a physicist is start to think about limiting cases or special cases where you think you might have a good idea of how the system is expected to behave, and then verify that your equations or whatever, you know, sort of analysis you've done gives you those results. To give you an example, we'll walk through a few of these. One is, let's consider special case number 1, the same sort of situation, ball 1 hitting ball 2, where the balls have equal mass, right? And if you've ever played pool or billiards, you've probably seen this. You have a ball that's stationary, you hit the cue ball at it, those have the same mass, and the cue ball will hit the whatever ball you strike. If it hits it head on, that ball shoots away and the billiard ball stays stationary. Well, what does our equations predict, right? So, well, v final x1 is just going to be equal to 0 because these two masses are the same. So that it essentially is saying that cue ball stands still after the collision. And you know, if you're familiar with that, that's a very that happens, and we're kind of predicting, our equations are predicting that's what happens. If what about the final velocity of ball two? Well, this is going to be 2 times m, and since these masses in the denominator are the same, it's divided by 2 times m, the initial x1. These cancel, and we have the initial velocity of ball two is equal to the initial or the final velocity of ball two is equal to the initial velocity of ball one. So we've essentially described the situation of those billiard balls where I hit the cue ball, it hits the billiard ball that's stationary, the cue ball stops, the billiard ball moves off with the same speed it was struck with, and our equations sort of tell us that's what's going to happen. So things seem to make sense. Another case we can look at is, let's imagine one of the balls is much bigger than the other ball. Imagine you roll a bowling ball at a ping pong ball or something like that, or a bowling ball at a beach ball, so they can be sort of the same size and bounce normal. Well, what happens? The bowling ball, you would expect the bowling ball to just keep going and not really notice that it bumped into a beach ball, and you would expect the beach ball to sort of bounce off the bowling ball and fly in the direction it was hit. Well, again, let's see what the equations we derived are, right? So the final velocity of the initial ball, which is our bowling ball, is going to be equal to m1 minus m2 over m1 plus m2, v initial rather, x of ball one. Now, if m1 is much greater than m2, right? We have, you know, let's say 10 kilograms and 10 grams, right? m1 minus m2 is essentially just going to be m1, right? If I take 10 grams off 10 kilograms, I have 10 kilograms still. Likewise, m1 plus m2 is essentially m1. If I take 10 kilograms and add 10 grams, it's still going to be essentially 10 grams. So what this means is this is approximately equal to just v final x1, right? Because that's going to be m1 over m1, which cancels. So we essentially get that prediction where the bowling ball would just keep going and not really notice it's hit something that's, that small. What about the final velocity of ball two? Well, we can use the same sort of analysis where this m1 plus m2 in the denominator is approximately m1, right? So what that means is this m1 plus m2 is going to cancel, and we're going to end up with 2 times m1, right? So the beach ball, say, that the bowling ball hit is going to bounce off and be moving at twice the speed. Oops. Over m1. I should probably finish writing this equation. And those cancel. Twice the initial velocity that bowling ball had. And so we predict kind of something that, if you can imagine that situation, we would expect. So another, way that our derived equations sort of match what we might expect from, given a situation that meets this limiting special case. The third one is sort of the opposite. What happens if I throw the beach ball at a bowling ball, right? Well, if I throw, or a ping pong ball at a really heavy bowling ball, or some really light object at a heavy object that's standing still, again, we're essentially just going to expect that light object to bounce off, right? It's not going to move the heavy ball. It's just going to bounce back. And our equations, turns out, do predict that correctly. The final velocity of that ping pong ball, say, that we've thrown at the bowling ball, is equal to m1 minus m2 over m1 plus m2 times the initial velocity of the ping pong ball, how we threw it with. if M1 is much less than M2, then that implies that M1 minus M2 is essentially negative M2, right? If I have 10 grams and I subtract 10 kilograms, I essentially get negative 10 kilograms. Similarly, we also have that M1 plus M2 is essentially just M2, right? 10 grams plus 10 kilograms gives me about 10 kilograms. So if I do that, this equation becomes negative M2 over M2, the initial x times 1. These cancel. And I have uh, the ball, the ping pong ball that I threw with some initial velocity Vix1 bounces back in the opposite direction with the same speed it had when it hit that heavy ball. What about the bowling ball that we threw the ping pong ball at? Well, 2m1 over m1 plus m2, the initial x1. This is going to be 2m1 over that m2, right? And because, again, the sum in the denominator is approximately m, so use the approximate m2 there. And since m2 is so much bigger than m1, this is going to be an extremely small number. You know, this is essentially 0. Where M1 is very small, 10 grams, say. M2 is really big, say 10 kilograms or 10,000 grams. So, you know, we're at a very small number here, essentially 0. And we've predicted kind of what we expect to happen in this sort of simple limiting case. I throw a ping pong ball at a bowling ball. The ping pong ball bounces back with the same speed I threw it, and the bowling ball doesn't move. And that's what we got from that's what we've derived as well. So again, the reason I like to look at these special cases is because it's a skill that I think is very valuable. The further you get into science in that, you know, we're using sort of our understanding of physical concepts to analyze and derive predictive equations, and it's often difficult to think and believe, at least with me, believe that what I've done is I haven't made any mistakes and that these equations and that are actually correctly describing things. And one way you can give yourself some confidence, well, the first way is just make sure the units work out. You know, that's a big check. But the other way you can do is think of limiting cases or special cases where you sort of know already how that system would behave, and then make sure that the equations and your analysis sort of agrees with what you would expect, what you know is going to happen. And we've done that for the 3 cases in this. So putting it all together, perfectly elastic collisions where we have one object is stationary before the collision. We have a stationary object hitting, one object traveling and hitting a stationary object. Knowing that it is a perfectly elastic collision tells us that the kinetic energy is conserved before and after. Using conservation of momentum and energy conservation, we derived these 2 equations that can describe those collisions. And now we can describe essentially all the collisions that we're going to cover in this course. The elastic collisions, where the objects bounce off and kinetic energy is conserved. Perfectly inelastic collisions, where the objects stick together and some of that kinetic energy is converted to thermal energy. And we can, applying these correctly or just using conservation of momentum will allow us to figure out whatever we need to know about those collisions. We'll go over some examples in class in our synchronous sessions. If you have questions, as always, email me and we will get through them.